Okay, we're going to do Chapter 5, Test A. So this one probably is going to be partial fractions because x squared factors out of that and leaves an x minus 4. And so this is like x minus 0, a linear factor, x minus 0, and x minus 4. We have a repeated factor. Now the way to do that is to put the first one with an a over it, the repeated one, instead of doing it over x, we do the repeated, we call it x squared, and put a b over it. And these are all linear factors, so we don't need to do bx plus c. And this one is c over x minus 4. Okay, and that's supposed to equal the x plus 4 over x squared times x minus 4. That is the common denominator. So to get x squared, I need to multiply by an x. And then to get the x minus 4, I need to multiply by x minus 4. So that's what I need to multiply the numerator by, x squared minus 4x. On the second one, I have the x squared, so I just need to multiply by x minus 4. And on this, I need the x squared. So, doing the identically equal, we have no x squareds equals ax squareds. I don't need to put the x squareds in there, and then no x squareds from this, and a cx squared. But I don't need to put the x squared, so a plus c has to equal 0. Doing the x's, I have 1x equals negative 4a. And I get x there plus b, and no x's there. And for the constant, I have 4 equals no constants here to take times a, negative 4 times b, and no constants there. Now I can put this into matrices. 1, 0, 1, negative 4, 1, 0, and 0, negative 4, 0, 1, 1, 1, but I can also, this one turns out to be pretty easy because negative 4 times b equals 4, so b must be negative 1. And if b is negative 1, we add 1 to both sides, we get 2 divided by negative 4, which is negative 1/2. And c, a plus c is 0, so if a is negative 1/2, c must be plus 1/2. So putting those in, I get the antiderivative of a over x plus the antiderivative of b over x squared plus the antiderivative of c over x minus 4. So the half comes out, and I'd have 1 over x. The antiderivative is ln x, so I got negative 1/2 ln x. The minus 1 pulls out, so I get minus 1. And this is just, it's not an x, it's not linear, it's x squared, so that's like x to the minus 2. So if I find the antiderivative of x to the minus 2, I add 1 to this, and that makes x to the minus 1, and I have to divide by that minus 1. And so I get minus 1 over minus 1, which is plus 1, and x to the minus is 1 over x. Plus the half comes out. This is a linear term. It's not 2x, so I don't have to divide by 2 or 3x or something like that. So it's just ln have the value x minus 4 plus c. Sorry, that was off. Okay. Now, I can also do this like some people did. They said, let's call this x squared an unfactorable quadratic, which means we'd put ax plus b in. Because if it's a quadratic, we do a linear factor over the quadratic. And then we have a linear factor, x minus 4, which we'd put a constant over. And if this is going to be equal to x minus 4, and this is the common denominator, I need to multiply this one by x minus 4. And this one by x squared. And if I do the matrix again, I get for the x squared, there's none. And I get ax squareds. And no b, no ax, plus c. And for the x's, which there's 1, I get, see, ax times negative 4, that's just a negative ax, negative 4 ax's. And we get b times x, that's plus bx, so b x's. And no x's from there, no others. And constant, I have 4 equals, and I get constant, see, a, that's got an x in it. Everything with a will have an x out of it. So the b times negative 4, and no constants there. And you notice I get the same thing. Now, how does this work out? Well, I get the antiderivative of ax. A turns out to be negative 1/2 x plus b, which is negative 1, over the x squared dx, plus c, which was 1/2, over x minus 4. Now, when I have something like this, if you do u sub, you're going to get a 2x, and it'll cancel there, but won't cancel on an x there, so it doesn't cancel. But the way you do this when you got addition, you want to split this up. So this becomes the antiderivative of 1/2 x over x squared dx plus a negative 1 over x squared dx plus the 1/2 over x minus 4 dx. And this x will cancel one of these, and I get it's negative 1/2. I get negative 1/2 x squared, which negative 1/2 over x, which I had there. I get negative 1 over x squared, which I had there. And I get 1/2 over x minus 4, which I had there. So this turns out to be the same answer. Okay, Number 2. Now you can do this with substitution, but this easily is done with tables. And the table that works with this one, if I do 11, the sign would stay the same and the cosine would go down by 2. That would turn into a negative exponent. We really don't want to do that. But if we use 12, then the sign goes down by 2, which should make it sign to the 0, or 1, which should make it disappear. And so that's probably what we want to use. And so that becomes, let's see, it makes m be 2 and n be 1. And so we get minus 1 less on the sign, so that was 2, so it goes to the sign to the 1. And 1 more on the cosine, so that was 1, so it goes to 2. Over m plus n, which is 3, plus m minus 1, so that's 2 minus 1, which is 1, over m plus n, 3 antiderivative of sine dropped by 2, so it goes to 0. Sine to 0 is 1. Anything to the 0 power is 1, except for 0. And cosine would stay what it was, which was a to the 1. So 1 cosine x dx. Which then is, we're not doing any integral on this, so it's just negative sine of x cosine squared x over 3 plus 1/3. Let's see, we take the derivative of sine, we get cosine. So it's just sine x plus c. Now, if we were to do substitution, we would let u be sine of x. So du would be, the derivative sign is cosine x dx. Divide both sides by cosine, we'd get du over cosine x equals dx. Replacing things, we'd have the integral cosine x, sine squared, that'd be u squared, and dx is du over cosine x. The x's would cancel. We'd have the integral of u squared du, which is 1/3 u to the 3rd. Going back to the x's, u was sine of x, so we'd have 1/3 sine cubed x plus c. And you can show that this and this are the same. Substitution was the easiest here. So if we do substitution here, we have to use the table someplace else. So let's go on. Let's see if we could have done that someplace else. Now this one's easy to do with substitution. We let u equals 4x squared plus 9. And du would be 8x. Divide by 8x, and we would replace dx with du over 8x. And this would become the integral of x. All of that would have been our u, and our dx would be du over 8x, and this x's cancel. The 1 over 8 comes out. 1 over u du, which is 1 1/8 ln of u plus c, and u was this, so we get 1/8 ln of 4x squared plus 9 plus c. So that's pretty easy with substitution. It could also be done with trig substitution. So if we do a triangle on this one, to get addition, we'd want the square root of 4x squared plus 9 on the hypotenuse, which means we'd probably want to put a 2x and a 3 here. We could do it the other way if we wanted, but that's the usual way to do it. So using those, the tangent of theta is the opposite leg over the adjacent leg. So multiplying both sides by 3/2, we get 3/2 tangent theta equals x. And if you were doing trig substitution by the way some people teach it, you would just put that in for that x and square it here and use trig identities to try to simplify it and come up with something you can do. But we can also just do it like I've been teaching in the class. We got to replace the d theta, and you would have to do that also if you were doing this. And so dx, the derivative of this side, would be 3/2 derivative tangent is secant squared theta d theta. And we'd have to replace this. That over 3 is the secant. Square root of 4x squared plus 9 over 3 is the secant of theta. So multiply both sides by 3 and we get the square root of 4x squared plus 9 equals 3 secant theta, but we want it without a square root, so we'd have to square both sides. So this would become the integral. Replace the x. That's 3/2 tangent theta. Replace the dx. That's 3/2 secant squared theta d theta. Replace that non-square root thing. Well, that would be this quantity, 3 secant theta squared, so that'd be 9 secant squared theta. If I do some simplifying, the secant squareds cancel, and I get, 9/4, which would come out of the numerator, and a 9 that comes out of the denominator, and I'd have tangent theta d theta. Now, at this point, I've been doing trig sub, but to do this, I could go to the table. So if I wanted to show that I know how to use tables, I could use the tables on this one, and I wouldn't have to call it a trig sub, although trig sub works. It also works with substitution. So we could come up with tables on this one, but it wasn't an obvious starting place. And the 9's cancel. We'd get 1/4, and the antiderivative, according to the table, of tangent of theta is natural log of the secant of theta, ln secant theta d theta. Plus c. We've taken the antiderivative, so plus c. But we need to go back to x's, so we want to look at the secant. Well, right here is the secant, but we can also just look at the triangle, and it's 1/4 ln. Secant is the square root of 4x squared plus 9 over 3 plus c. Now these two answers should be the same or very similar. So how could that be? This is an eighth and this is a quarter and so on. Well, if you know your log rules, the log of two things divided become the log, natural log of the numerator, minus the natural log of the denominator. And then we'd have 1/4, and this is ln of, and this would be to the 1/2 power, 4x squared plus 9 to the 1/2 power, and the half power would come down in front, according to another log rule. So we'd have 1/2 times 1/4, which is 1/8 ln 4x squared plus 9. And we'd have 1/4 times this, minus 1/4 ln of 3 is positive, so I don't need the absolute value, but I'll put it on there. That's a constant. This can all be redefined as a different constant, which is what this constant would be, and the rest of this does match. So the C here and the C here are different, but the crucial part is the same. So this is good enough, as is that. But remember, we got to show all 5 different methods. So if I do substitution, I got to do trig someplace else. If I do trig sub here, I got to show substitution someplace else. Now back here, I could do this one with substitution, but then I'd have to use table someplace else. So let's continue on. Now this one, there's no table for it. Can't do it with substitution. This one really needs parts. And the parts, we usually let that be the part that we take the derivative of. So if I put x here and the cosine x dx here, this down as v prime, and find v, so what we take the derivative of, that would be sine of x's derivative is cosine. And the antiderivative here, this would be dx, 1 dx, derivative of x is 1 dx. And the rule says that the product rule says the derivative of a product, x sine x, is the derivative of the first times the second plus the derivative of the second times the first. And so we've got derivative of the second times the first here, so we got to subtract the integral of the derivative of the second time, the first times the derivative of the second, which should be sine x. Or, as I've said in the before, those two minus, since we set these up, it's the other diagonal that goes here, the dx times sine x. And so this becomes x sine x. The antiderivative of sine would be negative cosine x, so the negative and negative makes plus cosine x plus c. Five. This one doesn't do well with substitution, can't do it with parts, can't do partial fractions when this is in a square root, and trig sub will work. There's nothing in the table, so this one's pretty much stuck with trig sub unless there's a different method along the way that we could use to demonstrate proficiency at. Okay, so trig sub would say, let's let, see, we got to have a 4 minus, so we're going to have to put 2 here, probably x here, so it's the hypotenuse squared minus the leg squared is the other, square root is the other leg, which should be 4 minus x squared, if that's theta. So doing the simplest, x over 2 is the sine of theta. Multiply by 2, we get 2 sine theta equals x. And once again, you could do this problem by then putting 2 sine theta in for that x and in for that x and doing trig identities to simplify it. Or you can continue on and find the derivative. We got to replace dx. You got to do that anyway. Derivative of this would be 2 cosine theta d theta equals dx. And to replace that square root, that would be adjacent over hypotenuse. That's the easiest. We could do over x, but hypotenuse is the easiest. That would be square root of 4 minus x squared is the cosine of theta if it's over 2. You multiply both sides by 2. That could be replaced with 2 cosine theta. So now we do the substitutions for trig. So we get the, let's do it here, the antiderivative of 5, x is 2 sine theta, and that's cubed, and the dx is 2 cosine theta, d theta, and the denominator is 2 cosine theta. Now many of you did that, but you left the x here. If we're going to be in d theta, we have to change to theta. So, and some of you said, got to here, but said this is 2, but it's 2 to the third, which is 8 times 5, 40. Antiderivative of sine cubed theta d theta. So now you could use the table to solve this one and say, I'm going to demonstrate my use of the tables on this one. Then that would be this formula, reducing it by 3. You can also do this one by substitution. So we could say I can demonstrate my ability to do substitution on this one also. And I'm going to do both of those here to finish it up. But probably the primary one here is trig sub. But anyway, doing this, n would be 3. So I would have 40 times negative sine to 1 less, so that'd be sine squared theta cosine x over n, which was 3, plus n minus 1, which should be 2 over 3, antiderivative of sine to 2 less, so that'd be sine to the 1, theta. Oh, and these are all thetas, even though this formula says for x, it's assuming the variable is x, but our variable is theta, so we need to have it all in thetas, d theta. And so we get 40 negative sine squared theta cosine theta over 3 plus 2/3. The antiderivative of sine is negative cosine, so I'm going to put the negative here, cosine theta plus c. I'll just do the plus c on the outside. And now I need to go back to x's, and I'm going to do that up here. So I'm going to look at my triangle. I can look here, and it says the sine of theta is x over 2. So sine squared is x over 2 is x squared over 4. So I got 40 negative. For the sine squared, it's x over 2 squared. For the cosine, it's this over 2. So that's the square root of 4 minus x squared over 2. That's the cosine. All that's divided by 3 minus 2/3 cosine. That's the square root of 4 minus x squared over 2 plus c, and I'm back to x's. Now, I could do this one with substitution. I could say it's 40 integral. I could think of this as the sine of theta times the sine squared, which is 1 minus cosine squared theta, d theta. And if I let u be cosine theta, du would be negative sine theta d theta. And so d theta would be du over sine theta. And you can see how the sine theta would cancel here. I'm going to get sine theta times 1 minus u squared. D theta would be du over minus sine theta. The minus would come out, make that negative 40. Integral of 1 minus u squared, sine thetas cancel, du, which integrates to be minus 40. The integral of of 1 is u. The integral of u to the second becomes u to the third times 1/3 plus c. Then we'd have to change back to u's back to cosine theta, so it'd be minus 40 cosine theta minus 1/3 cosine cubed theta, and then change back to the x's, which over here the cosine of theta is that square root over 2, so it's minus 40 cosine of theta, which is square root of 4 minus x squared over 2 minus 1/3, that same thing, square root of 4 minus x squared over 2 cubed plus c. And with a little bit of algebra, you can show that this is equivalent to this. Not easy, but it can be done. Okay, number 6. So if we got to take the derivative, it would be advantageous to call this capital F of t. So we take the derivative, we get little f of t, which we don't want to figure out, that we have to integrate from 3 to x dt. The antiderivative of little f of t is capital F of t. And we'd evaluate that from 3 to x. So, and capital F of t was this, so we put x in for the t's, and we get the square root of x e to the x minus, we put 3 in for the square root, and we get square root of 3 e to the square root of 3. That's it. And now finally, S of 2n, Simpson formula, is 2 of the midpoint rule plus the trapezoidal rule, O divided by 3. And if this is this is n. And since I wanted you to find S of 6, this has to be 3 and 3. So we need to find midpoint 3. So I got to split this into 3 equal intervals. 1, 2, 3. These both have to be the same. If I asked for S12, we'd have to do midpoint 6, and we wouldn't have the midpoint, so we couldn't do it. But midpoint 3 we can do. The midpoint of this first interval is 11. The midpoint of the second one is 4. The midpoint of the third one is 0. And the width of each of these is 0 to 4, 4. 4 to 8, 4, 4, 8 to 12, 4. So this is 15 times 4, which is 60. And the trapezoidal 3, the width is 4 again, if we're going to do this in 3, and the trapezoidal is the left and the right, so 12 plus 9 divided by 2, 9 plus 1 divided by 2, and the left and right again, 1 plus negative 3. Or you could do left 3, which would be 12 plus 9 plus 1 times 4. And right 3 would be 4 times 9 plus 1 plus negative 3. And figure this one out, add them up, divide by 2. Same thing you would get from this. These are all divided by 2, so I can go 12 plus 9 plus 9 plus 1 plus 1 plus a negative 3 divided by 2. So 9, 12, 21, 31, 32 minus 3, 29 divided by 2 times 4 would be just 4 divided by the 2 is 2 times 29, which is 58, which is what I should get if I found this one and add them up, divide by 2. I get it. 58 for the trapezoidal. So I have to do 2 of the midpoints. 2 times 60 is 120, plus 1 of the trapezoidal divided by 3. So that's 178 divided by 3. 3 goes in there, and that's 5 with 2. 3 goes in there, 27 would be 9, and 1 left over, and 1/3. So 59 and 1/3. It's in between these two, closer to the midpoint than to the trapezoidal. And that's how you do Simpson of 2n. These two have to be the same, and half of what that is. And that was 6, so those have to be 3's.